All good. So, Chris, the floor is yours.
Okay. So I guess I'm the last one for the break. So thanks for sticking with it. I'm really excited to have the chance to talk to everybody. So I'm mainly going to be talking about kind of resonator networks and my efforts to combine them for visual tasks involving sparse coding. This is work that, I'm hoping to push out as soon as possible. And I thought I would use this as an opportunity to collect some feedback and have some good discussion. So please, if you have questions or ideas or constructive comments, would love to hear any and all of that. I just want to briefly acknowledge, so I'm at UC Berkeley and the Redwood Center for Theoretical Neuroscience, and there's a lot of awesome people here, and I'm shouting out like a few of the people who are interested in like HT computing and VSA and kind of help me along the way. Especially want to point out like Annabelle, who's been helping, an undergrad who's been helping with some of the simulations for these sparse coding experiments, and of course you can see Dennis over there, like kind of by the bell tower. But very grateful for the kind of community and people that I've been able to talk to. So firstly, I want to motivate the kind of problem that shows up, and it's not just in vision, but it's this problem of factorization. So you might have already seen this like checkerboard illusion. So raise your hand maybe if you've kind of seen these squares before. Okay, so at least a few people, but I want to point out, so here it looks like in P and R, these are very different colors, right? Actually, in terms of the pixel values, they tend to be, they're the same. But the reason why they appear as different colors is because we're able to factor out the intrinsic color of the objects from certain lighting properties of the visual scene. And then once we have that, it explains away the difference from the image hitting the retina versus the objects that we're able to perceive. A similar kind of factorization problem happens in shape and motion, where the image that we're actually receiving that's on the retina is never constant at any particular time. Our eyes are always constantly moving around, and even there's like a little bit of drift. And then we have cones, so then there's color entangled up with all of this too. But the point of this is to say that even though the kinds of information that are coming into our visual system are constantly changing, the world appears stable, and it's kind of a miracle, if you will, of brain and its engineering that's able to do that. But then yet a third example is that we can recognize that all of these items are A and that these items have the same kind of font, even though if at a pixel-wise level, there's a lot of stylistic kinds of variation. So one way to think about all these kinds of examples of factorization is that there's multiple examples contributing to the initial data stream that we're given. They're combining in a nonlinear way, and that it's not simply just shape and then summed on top of motion information, but that they're entangled in some sort of way. And that it involves a combinatoric search problem, namely that if we were to search through all the possible sources of light factors and objects in the world and enumerate them and then say which one has the maximum probability, we would never be finished analyzing 1 second of information that we're receiving from the visual world. So this is all to say that we have a kind of challenging problem here, and it's a mystery as to how brains, people, but also other animals are able to navigate the world and make sense of all this kind of complicated information. So now I think it's an exciting time to be thinking about VSAs, because like resonator network is one particular algorithm that's able to solve these kinds of problems. So the idea is to represent this information that's being entangled together, such as like form and motion, or you can think of the most basic case of form and motion as a object or like a visual object and its position, so just the what and where information, and then also bound with additional information such as color, so that's this equation here, and then these are, so the exponent is to denote like fractional power encoding. And very grateful to Jeff for like giving a nice introduction to that earlier today, so I don't have to re-explain all of that again. And then I'll show you the kind of algorithm and the output of this in a moment, but I just want to point out that if you were to try and just do gradient descent on this, I mentioned this a little bit last night, you'd very quickly run into kinds of local minima where you get kind of spurious correlations that wouldn't kind of work as well. And so that's a reason why we think that resonators are able to solve search problems that in this case, this is a log scale, so about 2 orders of magnitude larger than a lot of other algorithms. And this is the work of Spencer Kent and a lot of very intense algorithms and trying out different dimensions and parameter searches to verify resonators compared to other kinds of algorithms on these kinds of problems. So I just wanted to show if I can, this demo that Paxton has of trying to infer a particular image or images from this scene. So each of these like y-axis terms are I'll just play it again, the like similarity or the vector similarity to particular items in the code book. So in this case, it's color, but then there's also 26 letters and then over 50 positions, both horizontal and vertical. So you can see in terms of the combinatorics of the search space, it's very large. But what the resonator is able to do is it's able to do this thing of searching in superposition for these solutions, where the idea is that if we had the right solution to the right factorization, then everything will be self-consistent. So if we know where the object is, then we can identify it. And if we know what the object is, then we could find out where it is. But then it's a chicken and egg problem, of course, of figuring out, one of these factors kind of first. And we could do it by brute force, but we might be just waiting for a long period of time. So now I'll walk you through the algorithm that the resonator works through. So this is just an example, and it works for bipolar vectors. Most of the cases I'll be working with are the Fourier holographic reduced representations, because phasors are very nice for representing fractional power encoding, and then you can use Hadamard product for the binding operations. But the idea is if we have three things bound together, let's call them X, Y, and Z. X can be from a set of codebook random vectors, as can Y and as can Z, and then we can concatenate them into our codebooks, which are big X, big Y, and big Z. Then the resonator consists of these three kinds, or these update steps, where if the Y and Z estimates that we have at the previous time step are correct, then B times Y inverse times Z inverse will get back exactly the correct X that we're looking for. And the same would hold true for the other variables, except swapping out Y here for X and Z. But then in addition to that, we need some kind of cleanup steps. So this XX transpose is projecting back onto your codebook. And then this G is a nonlinearity. If you've seen a lot of Hopfield network equations, you might think of it as a very similar update to the Hopfield network, except you're updating based off of the other factors rather than your state. And if you're using complex vectors instead of sign, you do amplitude normalization as well. But this is just, some of you may have seen this before, but I think, since we're at a VSA conference, it's kind of useful to go through, if this is the first time you're seeing a resonator, kind of an intuition of what the equations are doing. So now I'm going to move into the visual factorization aspects of this. I want to point out that if you've been to the VSA online talks, you've probably seen a lot of works working on resonators and these visual scene factorization efforts. And I want to say that there's a lot of good insights from these papers. And then, these talks are also worth checking out. One thing I want to emphasize as a difference between what I'm presenting now and what's been presented here is that a lot of the encodings that are being used, at least in these initial models by like Alpha and Paxton and others, are working with pixel-based encoding. So they're not learning any representations of the images. And then I believe in this recent work with the Ravens progressive matrices, it is using like a ResNet to go from the image to a particular HD vector encoding, but the HD vector encoding is decided ahead of time in advance to say, okay, the resonator network should go from, or the ResNet should go from this image to this particular HD vector. Whereas the focus of what I'm going to be presenting here is what's a good kind of principled way to learn what those vectors should be in a way that's adaptive to the particular data. I think there's something to be gained from learning the useful visual representations, even though you can go very far without explicitly focusing on that step. And then just to motivate a little bit more of the feature representations. So one reason why you might care about it is from a neuroscience perspective, or how is the brain representing information in a useful way. But then a different kind of way that I think is fundamental to HD computing is just thinking about the kind of capacity limits that distributed representations have. So we can keep superimposing information, but then it just becomes more and more difficult to encode. And then this is just like an example or illustration from this neurocomputation paper by Paxton, Dennis, and Fritz, kind of giving the quantitative theory about that. But we know that images are highly redundant, as are many sources of data. They can be more efficiently described in terms of a sparser subset of elements. So this is what sparse coding, you might also know it as dictionary learning, tries to learn. So these are just some example dictionary elements from the Olshausen and Field 1996 paper, trained on natural images. I'll go into the equations for this in just a little bit, but I think it's also interesting, if you didn't already know this, that these kinds of localized, oriented, kind of Gabor-like receptive fields are pretty similar to what people have observed from like electrophysiological recordings in visual cortex. And so at least for me, this is kind of an additional motivation to be thinking about how to think about how the visual system is able to solve these kinds of problems. It makes a nice connection to the like neurobiology by going in this direction. But now we get to kind of the heart of the new things I want to show you, which are kind of three connections between like VSA algorithms and sparse coding. So one is this bridge between like vector function architectures. So I'll explain a little bit about that, and a convolutional version of sparse coding. A second thing is how this can help, or sparse coding can help the resonator network solve inference problems a little bit better. And the last thing is related to the generative models for certain classes of sparse coding. This model that Paxton and Alpha have on, I guess, learning the transformations, whether this is rotation and scaling or 2D translation. There was also a VSA online talk on that from a while ago, so you may be familiar with that from there. So this is not the slide or the talk where I'll be explaining VFA, though I'm happy to talk to anybody who wants to learn more about this idea later. But the key point I want to highlight from that paper here is that it's kind of an extension of the VSA framework to go from fractional power encoding of continuous variables or scalars to functions. So the idea is really simple. It's that if you have a function that you can represent as a weighted sum of particular support points, so this alpha k could be the y value or the output of the function, and then the k is some kind of basis function or kernel shape, could be the sinc function, for example. And it turns out that this is a good way of representing many kinds of band-limited functions, so functions with a maximum frequency. Then we simply take this function and we can represent it as a vector, where the vector is a weighted superposition of these particular support points. So we just take this k, or this kernel representation, and then approximate it with a random vector. And then this allows for, just as we can have operations, such as addition operations on scalars, we can also have function manipulation as well. So we can read out particular values from this function representation. We can add functions, we can convolve functions, we can take function similarity, and then the operations for these are fairly simple. So addition, binding operations, and taking inner products. And I just want to point out that this linear summation model is actually very similar to the sparse coding generative model, where we're having a linear combination of our basis functions. So these are these like Gabor-like functions in the case of natural images that we're seeing before. But then in addition to that, we have an additional term that's in the energy function. So we perform usually gradient descent for sparse coding to enforce that the solutions that we're going to find are sparse. So one reason why this is often done for sparse coding is that the number of dictionary elements, or the set of phi that we have here, might be larger than the number of pixels that we have in an image. So it might be that we have 256 pixels in an image patch and 1024, for example, basis elements here, which means from a linear algebra perspective that there's a large null space. There's a lot of different ways in which we can create exactly the same reconstruction. However, they're not all going to have the same level of sparsity. And so that's how this term acts as a tiebreaker between those different possibilities that would explain an image particularly well. And so now to go into just some examples of looking at this into MNIST. So just to kind of set this up here, this is just the typical version of sparse coding, which can be working on an entire image or an image patch, and then you can work on this patch by patch. But you can also express this in a convolutional form, where you say that rather than have these dictionary elements like this, you have a feature map of these alpha or these A coefficients. You convolve them with this phi, and you want the alpha feature maps to be sparse. So then you say there's like a L1 norm in terms of yeah, these A's, which are now not like just one scalar, but 2D vectors. So just as like the simplest thing one can do, we can take MNIST data set as a very basic example. Here are some convolutional features learned on the MNIST data set. And so these features, I believe they're like 12 by 12, or so, whereas the MNIST digits themselves are 28 by 28. So even though we only have 8 features here, just remember that you can slide them around in different parts in the image, and they're going to be tiling the space. But unlike a convolutional neural network, there's an explaining away, or there's a competition between the elements. So as you can see, if we have a particular image and we have a sparse reconstruction, the coefficients are going to be a lot sparser than the original image. So what this helps with effectively is that we have less items in superposition in our hypervector. And it means that we're going to have a much, we're going to be more likely to be below the capacity limit in terms of what we can decode from our particular hypervector. And then in addition to that, with the resonator network, we can, for example, have a particular image where we have a particular digit. This can generalize to having multiple digits, but this is just as kind of an illustrated example where we need to figure out what the object is and then what its position is in the 2D scene. So the way to read these particular diagrams is to say, these are the different possible objects that we can have in the scene. So here, this 0 literally means the number 0, whereas here, this X position is one of the particular shifts that it could be in this particular visual scene. And then the Y dimension is the iteration. So it's a discrete time update. So once it converges to the right solution, or converges to a stable solution, so it's no longer updating, then we just stop the simulation. Then in this kind of case, I think there's 2 kinds of nice things to point out. So the first is that in terms of the number of updates, so here's the kind of comparison. So these 2 sides are exactly the same, except one is using the convolutional sparse coding version of the image, and then the other is using the pixel encoding of the image. The yellow here is to indicate that it's highly similar to a particular solution, whereas the purple is saying it's pretty close to orthogonal to a particular item in the codebook. Okay, so 2 observations. One is that the iterations on average tend to be shorter for the convolutional feature encoding versus the pixel encoding. So just in this example, it happens to be 3 iterations versus 5 iterations. It's going to be random based off of your initialization. However, on average, it tends to be faster with the convolutional features. But in addition, and perhaps this is why, the features in this convolutional space are going to be less orthogonal in this space compared to in the pixel encoding, where if you just imagine the correlation between 2 random images and then take their correlation, there might still be some, versus projecting to this overcomplete sparse coding space first, where there's not likely to be similarity between the images, even when there's pixel similarity, because there's different basis functions explaining those different images. You can see that the objects look more orthogonal to each other in this particular space. So this is an advantage of the convolutional sparse coding over the pixelwise encoding. One thing to note is that at least in like previous models with pixel encoding, the standard thing to do is to whiten the vectors or to orthogonalize the templates in order to get around this problem. The difficulty with this, of course, is that when you whiten them, you're doing that with respect to a particular reference frame. And then when you shift the image, or you're working with a translated version, for example, there's no guarantees in that new space that it's going to be orthogonal to other shifted examples or even to your original ones. Okay, so the last kind of connection I wanted to talk about is learning kinds of group transformations with sparse coding and these these resonator networks. So in comparison to this model where we just have phi's, so dictionary elements weighted by alphas or a's, in this version we also learn Chowdall learned this group model for sparse coding. So this is representing a kind of transformation. So these W transpose and W's are orthonormal rate matrices, and this R is a 2D variable expressing the parameter, and it happens to be diagonal. In this case, they're working either with a case where the images are translated in 2D, or they're rotated and scaled. So there's also 2 degrees of freedom. And since these columns are orthonormal, or the columns are orthonormal, but then there's the task of learning what the right bases should be. And you might notice that these kind of patterns might look familiar, or they kind of, I hope, look something like a Fourier transform of these particular images. And this is exactly the right intuition to have, which is that what this W transpose matrix is doing is it's doing something like a Fourier transform of this particular image representation. Then it's shifting it by a certain amount. So the nice thing, as you might know from like Fourier, like convolution theorem, is that this convolution in the space domain and Fourier domain can be done by element-wise multiplication. But this is just a blocked diagonal matrix. So this is equivalent in this case to doing something like a kind of Hadamard product multiplication. And then this W just projects you back into the original space. So I think this explanation, I realize, is a bit fast, but I just want to motivate. This is exactly the same kind of model as what like the 2D translation or rotation scaling model that like Alpha and Paxton are doing. The nice thing here is that they're learning what the transformation should be. But the advantage of like a model that like Alpha Paxton have is that it's better able or quicker at doing these kind of factorization tasks. So with that, I have these kinds of 3 connections again. So just went over the last one about the generative model to like learn these transformations, but then also emphasizing sparse coding is able to help with the resonator, and this is all like mathematically possible thanks to like HD representations allowing for useful function representations, and this is what the like VFA kind of theory hopes to bring out. If people are interested, I mean, and I'm happy to take questions on this, but I'll stop in like 1 minute. There's ways of better being able to do this factorization via these kinds of residue number system ways of doing these resonator number systems. So it turns out that if instead of solving this 3-dimensional factorization problem, you can break this component down into 3 more. You can save in terms of the codebook entries and then the actual time to run the resonator as well. This would be its own presentation, so I'll just leave that as a kind of teaser, and happy to stop now and take any questions. So thanks for your attention.
Thank you, Chris.
Jeff, I saw your hand, and then
Play one. Did you ever solve for translation and rotation scaling at the same time, or is it one or the other?
So the difficult thing, as you probably know, is that translation and then rotation scaling don't commute with each other. So the way that Alpha and Paxton do this is they enforce that either the translation happens first and then the rotation happens. And then you can solve for both of those transformations and then do kind of a log polar transformation. I haven't specifically looked into, I guess, building things to that. So that's, I guess, a future work kind of section, but that's the kind of general limitation. The general limitation of the math is the non-commutativity. And then the difficult thing from the VSA perspective is that there are a lot of, for example, if you take a M and then you rotate it by a certain amount and then are also allowed to translate it, it might look like a 3. Just as a kind of example. And so then there's a lot, because you have so many degrees of freedom, there's it's very difficult to figure out, okay, what's the like true correlation, or what's the correct factorization versus one that looks very close. And maybe that's a feature, not a bug, but it makes trying to find the ground true state a little bit difficult.
So I think I have a simple question. On the resonator network algorithm, could you flip to your slide at the beginning? It's the one titled resonator network algorithm.
Yes.
So to try and understand this, I mean, this algorithm is, I love it. It really resonates. And what I'm wondering is, I can see a brute force algorithm for just computing the same thing. You can expand your code books, take the product, and then just compute the similarity of your B to each possible product. And you can pretty easily calculate the number of multiplications you would need, the number of arithmetic operations you would need to do that.
Mhm.
And then the resonator algorithm for solving this, does it involve less computation or more?
Yes, so you're completely right that you could do that. Let me just give you some kind of back of the envelope numbers or calculations that I've seen when running these algorithms. So if you just start with an example where there's 150 possibilities for X, for Y, and for Z, then you could do it in 150 cubed comparisons. On the other hand, with the resonator, you're doing a comparison with every item in your codebook times the number of codebooks that you have. So you're paying 450 searches per iteration. So if you're able to do 150 cubed over 400, or less than 150 cubed over 450 iterations, then you would have a savings. And in fact, yeah, it works, I think, on the order of like 10 to 20 iterations often. So then I think, yeah, that would just be kind of one case about the savings. Of course, the interesting thing is not how well does it work on like a particular fixed dimension, but how well it scales, both with the dimensionality of the problem, with the dimensionality of your hypervectors. And yeah, I think that like I would point to like Spencer's paper as having like so many of those kind of good experiments, checking what the scaling properties are, because it actually depends not just on the problem size, but also when you have more resonator factors, it becomes a more difficult problem as well. But I'm pretty confident that it would be a savings compared to the kind of brute force search that you have, because you just have less comparisons.
I think
Not sure who's next. Yeah,
I think Madison.
yeah.
So you moderate, so you choose to whom you want to talk to.
So I was wondering, can you bias the factorization procedure in certain regions, or are you forced to always have a very flat prior across all your combinations?
Oh, you certainly can. So I'll give you a quick aside to kind of answer this question. So if you notice what this X transpose and this particular vector, what it's doing is it's computing a lot of inner products, and then it's putting it back into the space. And then if you just put this G and call it something else, like, I don't know, softmax, and then you project back, it might look like something that you've seen in other kinds of contexts. Do you see where I'm going? Yeah. Yeah, but
I'm wondering, like, that kind of XOR-ish problem, like, I don't know, pink elephants, distinction, not pink elephants, but I'm trying to think of another point, but grey elephant should do, but grey pavement it should, pink pavement it shouldn't, or something like that. As in, surely that would kind of, you would be limiting favouring certain regions that are aligned with region dates rather than like arbitrary. That would be very cool.
oh yeah, so you would prefer certain kind of combinations
Yes,
over
any
others.
case of, like arbitrary combinations, or you being like one of your factored spaces.
Right. So yeah, if it's the factor spaces, then it's easy to see because you can add other kind of weights or nonlinearities here. In general, I think one thing that's relatively underexplored is like where the start or the initial conditions should be. So sometimes it's set to be the average of these codebook vectors, but you can also start from random, and it works particularly well, or almost just as well in like many cases. And if it doesn't, you can pick a different random initialization, and often will then kind of converge, or which is an interesting property. Dennis pointed out that this sort of like looks like what like a Las Vegas algorithm is doing, where once it runs, it has a certain kind of probability of success. So then my short answer is bias the initializations to be superpositions of the states you think are favorable. And if those are the true answers, then or they're well explained, they well explain this composite vector, then use it. Yeah. Oh, yeah.
Yeah, Chris, okay, leave it on that slide, please. First, I need to clarify something. With when you're talking about the convolutional encodings and so on, rather than pixel,
Yes.
you're treating that entirely as a fixed pre-processing step. Would that be correct? So you might do some sort of search to find a good set of transforms, but that's then effectively fixed relative to the time scale of the iteration of your resonator. Is that right?
That's how I'm treating it. Yeah.
Okay, yeah, all right. So with the resonator here, each leg of the resonator is effectively estimating a transform. It's the transform which takes the entangled input representation to an element of the code book for that leg, right?
Yeah.
And so you can view the elements in the code books as being HDC representations of functions which could be applied. And effectively you're searching over this, you're searching for a composition of functions which does what you want.
Yeah.
I was wondering, could you, and the elements in your code book, you're conceiving as corresponding to values of dimensions or something like position and color and letter identity and so on.
Yeah.
But I was wondering whether you might be able to actually stock the code books with VSA representations of convolutional features, because they're basically transforms of the input pixel space to something or other else. And so you're searching for a composition of features which neatly decompose the input data.
So you just decompose the image or something,
But into terms of features, rather than into some arbitrary external categories you've defined.
Right. I'd like to think more about what the right way of doing that would be, because conceptually, I think that's right, that you would be able to do that in terms of, like, the nice thing about saying, okay, we have positions and then we have particular objects and colors, that we can write it all down and we know, like, what the right truth is for, like, the code books and so forth.
But it's an external thing provided by the programmer rather than something that's sort of inherent to the data stream.
Right, or being able to learn what the code books are in general, I think is like kind of the question that I find really interesting. And then maybe it is the case that positions and so forth are the right way to factorize the data, but it might not be. And I think learning that would just, I'm basically saying, yeah, I think it's a good question. And yeah, I think it's tricky how to like learn these things. Yeah. Oh, do you have a question as well on that?
Yeah. So how does this convolutional feature encoding affect the similarity distribution?
It basically pushes things further out into, or things that might be similar into the pixel space might be different in terms of the new HD vector that's representing them. And just to give you the intuition of why, like, you can see this vector and or this particular basis function and this one, they have some overlap. They're not exactly the same, but they're doing something similar. So in the pixel space, if you just had a particular image explaining, or that looks like this, it might have a high inner product with this particular, an image that had just part of the particular one. But in the sparse coding space, they're competing. And so then if you only had the list of coefficients, then you wouldn't know that those two images were similar. So what this algorithm is effectively doing is to say, okay, we could reconstruct the image and get the similarity out. But really what we want to do is push these two images into different parts of the space so we can better tell them apart.
I have rather maybe too detailed question, but just to increase my understanding, if you can change to the slide with this factorize interposition and ladder, and this the bar graphs. No, not that.
Oh.
One, but I mean the later on. So you're similar to that one. Yeah, this one, for example. This X and Y position, are they, I mean, kind of specific coordinates, or it's a span of along X and Y axis?
Yes, it's actually,
I simply don't see. So what is it?
so what it is, it's a FPE vector of different positions or scalars. So the way I think about it is that, like, the simplest function you can have is a delta function, because it's just an encoding of one scalar or one particular point. And so then when you bind a delta function at a particular location with the image, then that results in shifting the image.
Yeah, but I mean,
I
mean, so if you have, so in this case, 0.
Yes.
So this X and Y position, are they kind of correspond to the center of this 0, or it just it's a span over all the features of 0 in the scene?
Oh, so what it corresponds to is all the possible like horizontal shifts of the image or transformations I could have. So in other words, this like 20 position corresponds to let's just say if there was no X or Y bound to the vector, then the 0 would be in the top left corner. Like let's just say that as arbitrary reference frame. Then if we find X vector that is a FP value of 40, then we would shift it over by 40 pixels. And then we just take all the FPE values at the different.
I mean, I understand the mechanics of FPE, how you do encoding. I mean, I'm just maybe not fully comprehend the actual implementation. So you have a visual scene. So at what stage you actually do encode these bindings, X and Y? So, I mean, so you have a visual scene, say 250 by 250.
Yes.
And then you have some objects somewhere on the scene.
Oh, yes.
And then, so how do you do the encoding?
Oh, good. Okay. So here's the full pipeline. You get the image and it's just your usual set of pixels. Then you go to the sparse coding space. So now you have a stacked list of feature maps.
Yeah, that's I understand. So the code book.
Yes.
Yeah.
And then for each feature map, you encode some, random or some HD vector and then bind at the active location. So just take one feature map at a time. So bind HD vector corresponding to that feature map times position.
Actual position.
Yeah, XY positions of the feature maps. And then do that for all active pixels.
Okay.
Yeah.
And then somehow they all together they form I mean the zero number.
Yes, right.
Okay.
Yeah.
And if you have say several items on the scene, so it will be kind of like a binding or a superposition of this all features, right? So you cannot.
That's correct. Yes.
I'm just trying to understand it.
Yeah.
The reason, because in I mean very often there is a phase where you just extract a single object, so it's already centered, and you try to kind of and here you kind of encode a scene from the beginning to the end.
Yes.
And then it's kind of a mixture of all the objects on the scene.
Yes.
So how do you differentiate between them?
I just have a different example to make a similar point where there's two objects here and this particular spatial arrangement isn't something in the code book, of course. So what in this case the resonator network does is first it converges to one object, not some mixture of two objects. So in this case, the closest is index 0, which happens to be it finds the F first, and which is in the top left corner. And then you subtract that away from the vector and then run it again. And then in this case, it converts.
Okay. So there is always kind of sequential elimination of determined object, converged objects.
Yeah.
From
So
the scene.
when there's
it's not that you encode like the entire scene. That's
the thing. The resonator only knows how to search for things in the code book. So when there's actually a mixture of different items or a superposition of multiple items that could be in the code book, it's very interesting that it doesn't go and say, well, I'm getting half of a F and half of H. It just goes directly to one of these, even though the input is actually the sum of them. But then when you subtract away that solution,
of course,
it goes to the other. I think that's a greedy way to do it, and there's probably a better, more principled way of trying to figure out both at once. But the greedy thing, it does work in some cases.
So just to clarify, the code book in this case for the pixel-based version for a character is essentially a pixel map image of a particular character, so that it's ultimately it's just, as far as it's concerned, it's a pixel by pixel match to the shape of the character.
Yes.
Yeah.
Okay. Any other questions, or are we?
We're all happy.
All right.
All right.
Great.
Then we